In today's lecture, we will be discussing about the formulation of a pharmaceutical suspension and the stability considerations. How can we improve the stability of a pharmaceutical suspension by considering the electrical properties of suspended particles? This lecture includes the application of electrical properties of suspended agents to improve the stability of a pharmaceutical suspension formulation. In this lecture, we will be considering the electrical properties of suspended particles. For every suspended particle in suspension will possess some charge as they are finely divided particles, and this charge is technically known as zeta potential, the potential that is carried or that is seen on the particle surface, suspended particle surface. The overall potential existing on the suspended particle is known as zeta potential. Now here, how this zeta potential is applied to study the stability of a formulation, especially the suspension formulation. In a deflocculated suspension, all the particles will exist as individual particles. Because of a higher zeta potential. Now, because of this higher zeta potential, all the particles will be experiencing repulsive forces. Now, let's see here. Now consider this as a beaker having positively charged drug particles. Now these particles, drug particles having positive charge or same charged particles, they will have repulsive forces. So that all these particles will remain as individual entities and they will not have any attractive forces. Now we can say that the overall charge or the potential that is possessed by the particle is higher, and that charge is known as zeta potential technically. And if zeta potential is higher, they experience a repulsive forces. So zeta potential is more, repulsive forces are much higher or more when compared to attractive forces, and hence the particles remain as dispersed as individual particles. There will be no attraction or attractive forces between the particles. Now let's see what happens. How can we improve the stability of this deflocculated state or deflocculated suspension? Now let's consider a beaker with positively charged drug particles. Now these drug particles, because of the charge possessed by each particle, they will have or they will experience repulsive forces. The repulsive forces are more when compared to attractive forces, and hence the zeta potential will be more, and all the particles will be existing as individual entities or particles. Now let's see how can we improve or how can we bring flocculation in such type of um, formulation. Now to this system having positively charged particles, if we add electrolyte or any solution that is having opposite charge of the drug particle. Now in this case we have chosen drug particle having positive charge. Now for instance, if we are adding electrolyte having the opposite charge, like say negative charge, what would happen to this system? Now because of this oppositely charged particles, they will experience attraction forces or the attractive forces between the drug particles. Now, because of this, they'll experience attraction forces, attractive forces like this, like this, so that they'll form a network of drug particles. A loosely formed network of particles is seen because of addition of electrolytes. So because of this network formation, the zeta potential or the overall potential or the charge that is existing over the drug particle reduces because of the forces. So the zeta potential decreases and the attraction forces becomes more when compared to the repulsive forces, and that is how flocculation occurs. So that is how flocculation is seen. Now, what if in case we increase the quantity of electrolytes? So at optimum concentration of electrolytes or oppositely charged particles, this solution or these particles will undergo flocculation. But what if the concentration of electrolytes exceeds? If it exceeds, means there are more oppositely charged particles. Rather than formation of flocculation or floccules, the particles will undergo repulsive forces. Let's see how. Now, let's see how the concentration of the electrolyte helps in maintaining the stability. So, say we are taking the positive charged drug particles and we have added the negative charged particle or the electrolyte. Now if we have added an optimum concentration, the attractive forces will be higher when compared to the repulsive forces, and thus flocculation occurs. What if we have increased the concentration of electrolytes? Now because of increased amounts, let's see what happens. So because of this, all majority of negatively charged ions, they get added to the positively charged drug particles, and at the same time there will be all these particles will be experiencing the negative or the repulsive forces here. So rather than having attractive forces between the particles, here the repulsive forces will be will be more than the attraction forces or the attractive forces. That is how repulsion takes place. And that is how the flocculated suspension again becomes deflocculated. So it is necessary that the electrolyte that we add should be first of all the opposite charged particles, and again the concentration should be optimum enough. That is the importance of adding electrolytes to decrease the zeta potential, and that is how we can improve the flocculation, and that is how we can improve the stability. Now, keeping this concept in the mind, now let's see the theory behind the formulation of a stable suspension. Now, to let's see formulation of suspension. Now, in this formulation, to get a stable suspension, we are having two approaches, two ways how to improve the stability of a suspension, how to formulate a stable suspension. The first one is use of structured vehicles. The second one is controlled flocculation. These are the two major strategies by which we can improve the stability of a suspension. There is another way. The third approach is the use of the first two approaches, like controlled flocculation with use of structured vehicles. Now let's see one by one. The first one, use of structured vehicles. What is a structured vehicle and how it helps to improve the stability? Now, the name itself indicates vehicle is the dispersion medium which carries the dispersed particles. If we increase the viscosity of the dispersion medium, then the particles will experience some resistance to when they are getting sedimented. So here the viscosity of dispersion medium plays a major role. Viscosity plays a major role. So we should make sure that we need to improve or enhance the viscosity of the vehicle or the medium so that the deflocculated particles or the particles which exist as individual entities, they cannot settle down at faster pace because of the viscosity, increased viscosity. And again, by means of addition of suspending agents, also we can improve or we can sustain the stability of a suspension. So the major approach in this method is by the incorporation of structured vehicle, nothing but the suspending agents. For example, gums, sodium alginate, sodium carboxymethyl cellulose. All these are the agents which improve the viscous nature of the suspension or the dispersion medium. So the thixotropic behavior of a suspending agent actually helps the particle to remain suspended because of its higher consistency, because of its higher viscous nature. So here, basically in this approach, we are making the particle to undergo suspension because of improved viscous nature. So there is one disadvantage in this kind of approach, in this kind of method, is that in spite of increasing the highest viscosity or the consistency, the flocculated the particles or the deflocculated particles, they will form a cake. All the particles will remain as a discrete or separate entities and they'll undergo sedimentation. They undergo cake formation. This is the disadvantages of this approach. So, how can we still modify the way to improve the stability? Now, let's see. Now, the first approach is the use of structured vehicle. Yes, it improves the stability, but on long standing, there will be a cake formation because here flocculation is not seen. It is just we are improving the viscosity. Now, let's see a different approach where this disadvantage can be overcome. And the second method is the controlled flocculation. So the name itself indicates here, in this way, in this method, we are improving the flocculation. Here we are improving the particle loose aggregation so that the stability increases. So here, so to promote flocculation, there are two methods. First one is by decreasing interfacial tension, and the second phase is prevention of hard cake formation. So now we are discussing about the second strategy by which we can improve the stability of a pharmaceutical suspension, in which comes the controlled flocculation strategy. Now this method includes two stages. The first stage is by reducing the interfacial tension and by preventing hard cake formation. Now, how can we reduce the interfacial tension between the particles and the vehicle or the dispersion medium? By addition of wetting agents. So, this is by addition of wetting agents. Wetting agents, for example, polysorbate 80 and hydrophilic substances, surfactants, hydrophilic polymers, all these are used to reduce the interfacial tension between the solid particles and the vehicle. That is how we can improve the wetting nature of a particle, and that is how each dispersed particle will be wetted by the dispersion medium and will be able to have some attractive forces between the particles to undergo flocculation. So the first stage is we need to improve the wetting nature of the particle. So to improve the wetting nature of the particle, we are having different ways to improve the wetting nature by addition of wetting agents, by addition of hydrophilic substances which include glycerin, propylene glycol, alcohol, by use of surface active agents like wetting agents, hydrophilic polymers like gums and acacia. So now these have a greater advantage and also disadvantage, like gums especially, they act as wetting agents and also helps in improving the viscosity of the dispersion medium. So this incorporation of these substances will actually promote wetting nature and promote the viscosity. That is how these substances play a major role in improving the stability of a suspension, and at the same time being a natural origin, these substances are more prone for microbial growth, so it is a must to include preservative in the formulation. Now the second phase of controlled flocculation is how can we prevent the formation of a cake. Now in this phase we will be adding electrolytes so that the electrical barrier between the particles will be reduced and there will be decreased zeta potential, and attractive forces exist between the particles and thus forming loosely connected floccules or loosely arranged floccules. So the second method where we will be considering a controlled flocculation has two stages. One is reducing interfacial tension by use of wetting agents, and the second one is the prevention of hard cake formation by addition of electrolytes. So in this method is said to be more stable strategy by which we can improve the stability, because here in this method we can decrease the interfacial tension and also at the same time we can prevent the hard cake formation, because we have considered the electrical double layer concept here, and again we have added electrolytes having opposite charged to that of a drop particle, so that the attractive forces exist, more attractive forces exist than compared to the repulsive forces, and that is how the controlled flocculation is seen. Now let's see how this actually can be explained. Let's take a beaker, and here let's consider an example having bismuth subnitrate in water. So here bismuth subnitrate is the suspended particle and water is the dispersion medium. Water is a dispersion medium. Now let's consider the particles having positive charge. So all these particles, these bismuth particle is positive charge, and they have a higher zeta potential and they experience strong repulsive forces. Now when we leave this as such in water, now what is the fate of this bismuth subnitrate in water? Because of this repulsive forces, these particles will exist as individual entities and they will undergo hard cake formation. They'll undergo sedimentation and they'll stuck together to form a hard cake. So now we being a pharmacist, we should make sure that these particles should exist as floccules. They should exist as loosely formed aggregates or floccules, and that phenomena is known as flocculation. We being a pharmacist, we need to incorporate a substance like electrolytes having opposite charged particles, so that all these bismuth particles will be held together. See, so if we consider this, two particles are held together by electrolyte. These are held together by electrolytes, right? And see if we have this, these are held together by electrolytes, and that is how all the particles are held as a network together. So in this example here we have considered bismuth subnitrate in water. Bismuth subnitrate is positively charged particle. Now to this deflocculated system we are adding monobasic potassium phosphate, means a negative electrolyte, negatively charged ionic particles are being added to this system. So there will be a neutralization of the positive charge, the bismuth subnitrate particle, and thus the zeta potential decreases and it becomes zero, And it is at this phase where the attractive forces exist between the particles. So, this is called flocculation. Now, the concentration of the electrolyte also plays a major role. As we have discussed, the concentration of the electrolyte also plays a major role. It should be optimum enough. Now let's see. The control flocculation. So if we keep on adding electrolyte in more concentrations, then the control flocculated suspension turns out to be deflocculated suspension again because of more repulsive forces again. So this is another way by which we can improve the stability by reducing the zeta potential. Now let's see the third way or strategical method by which we can improve the stability of a suspension. The third method is the combination of the first two strategies, controlled flocculation and also use of structured vehicle. Then we can get ideal suspension or a formulation. The second strategy is mostly followed. The third one is widely used in pharmaceutical industry to get a stable formulation. Here in this, we'll be making use of both the viscosity enhancers or the thickening agents like carboxymethylcellulose, all the gums to get a higher viscous dispersed medium. It is also known as structured vehicle. So here even the structured vehicle charge is also to be considered. Here we'll be making use of a controlled flocculation phenomena and the use of structured vehicle. For example, this can be easily and can be explained by an example. Suppose if we consider a positively charged drug particle, it has to be flocculated with anionic electrolyte. If we are considering positive charge drug particle, it has to be combined with an ionic electrolyte, opposite charged electrolyte, so as to get a stabilized formulation. And in this method strategy, we are making use of controlled flocculation and also structured vehicle like the addition of gums or addition of polymers to improve the viscosity. Suppose if we have considered gums, right? So majority of the gums or naturally available gums or negatively charged gums. Now in case if we add negatively charged gums, it's fine. We should make sure that the electrolyte and the gum concentration should be in such a way that it should not exceed the optimum concentration. But if in case if we select not gums as an viscosity enhancer, if we select gelatin or any other substances like for say gelatin is positively charged. So we cannot use gelatin in this case. Why? Because even though it improves the viscosity, we cannot make use of because here the gelatin carries positive charge. So our aim is to nullify the positively charged drug particle. We should not add positive charged particles again to the system. So we should be really careful enough. We being a pharmacist, we should make sure that we should make sure and we should make note of the charges carried by all the ingredients that we use in the formulation. So that is how even the electrical properties of each particle in the formulation plays a major role in studying the stability of a suspension. That is why it is given with an example like negatively charged particles when they are flocculated with positively charged electrolyte, like aluminum ions, will be incompatible with the gums. Now, we should make sure even the selection of each ingredient plays a major role based on the charge it carries. Now, this entire explanation is explained in this figure, where we are able to see the drug particles, positively charged, negatively charged, or the neutral, addition of anionic electrolytes or flocculating agents, right? So they'll form floccules. Positive, negative charge will come together and they'll form floccules. Now in the next step we'll be making use of addition of suspending agent so that all the floccules will be suspended. So we are promoting flocculation and we are improving the viscosity and thus improving the suspending nature of the particle. So it is a combination of two strategies, the addition of a structured vehicle and also promotion of flocculation. That is how we can improve the stability. So this is how we, being a pharmacist, we need to make sure the selection of each ingredient plays a major role in improving the stability of a pharmaceutical suspension. Now we will be discussing about the rheological considerations of suspension. Now let's see and how it actually helps. Now, is it really important to study the rheological properties of a suspension? Yes, we being a pharmacist, we need to know how the viscous nature of a suspension plays a major role. Now let's see. As we all know, from the customer point of view, we should prepare a formulation in such a way that it should be easily pourable. If we are considering a liquid dosage form, we should make sure that it is easily pourable out of the container. And it should be easily spreadable over the skin if it is supposed to be for external use. So here the viscosity of a suspension plays a major role. We need to make sure the viscous nature is sufficient enough to prevent the settling or sedimentation, and also it should not be too viscous that it cannot be applied. So it should be having optimum viscosity so that it has good flow property. It should be easily pourable out of the container and it should be easily spreadable over the skin if it is applied over the surface of the skin. And the most important point is that it should have pseudoplastic behavior along with thixotropic behavior. Now let's see how the pseudoplastic behavior and thixotropic behavior plays a major role in improving the stability. The name itself indicates that the pseudoplastic behavior and thixotropic behavior is that there should be some change in the viscosity upon stress application. Means what? There should be some change in the viscosity when we shake the container. So for example, if we have taken a container having a suspension and we have kept it aside for some time, it turns out to be very thick in nature. It undergoes sedimentation, and if it is a flocculated suspension, of course, it will undergo a slow sedimentation, having a greater sediment volume. And when we shake the container, it will be easily redispersible. All the sediments will be easily redispersible. And the viscous nature of the formulation will be reduced. Right? Now, hence, when we keep the product aside, it should become or it should be thick so that a complete settling is not seen, rather a flocculation is seen. And upon shaking, it becomes less viscous and it helps in easy pouring and correct dosing. So here we should make sure that it should have pseudoplastic behavior and thixotropic behavior so that settling is prevented, so that it becomes easily pourable and hence it results in correct dosing. Suppose if the formulation is very thick enough and if it is not easily pourable, so all the drug particles will be sedimented and it is only the dispersion medium a patient will be or the consumer will be consuming. So there will be not correct dosing of a drug, especially in a deflocculated suspension. Hence, we need to make sure that the suspension should follow pseudoplastic behavior and thixotropic behavior. So that it should prevent the settling nature, it should prevent the settling of the particle, and it should be easily pourable when we apply stress by shaking, and hence it will help in correct dosing. So that is how stability of a pharmaceutical suspension can be improved by considering electrical properties of suspended particles, and also the rheological behavior. By correcting the rheological behavior of a suspension, we can improve the stability of a suspension, and thus we can improve correct dosing. We can promote correct dosing of the drug when we consider suspension as a dosage form. So in this lecture we have discussed about the rheological considerations, the stability, how can we improve the stability and sustain the stability of a pharmaceutical suspension by considering the electrical properties. If you have any doubts, you can contact me through mail. Supporting material for this video will be uploaded. Go through the video. If at all if you have any doubts or questions regarding this, you can ask me. Thank you.